In the late 20th century, two nearly identical white spaceplanes came to symbolize very different stories about power, paranoia, and engineering discipline. One was NASA's Space Shuttle, rolled out under bright television lights in Florida in 1979 and first launched in April 1981. The other was the Soviet Buran orbiter, mated to the gigantic Energia booster, and launched from Baikonur in November 1988 on a single, fully automated test flight. On the surface, they looked like twins, but the decisions hidden under the tiles and tanks reveal why one system limped on for 3 decades, while the other flew once and then literally disappeared under a collapsed hangar roof. By the early 1970s, NASA had reached a strange kind of victory hangover. Apollo 11 had landed on the moon in 1969, and by 1972, the last Apollo missions were already being canceled. Congress no longer saw the point of planting more flags, and public attention had drifted away. To survive, NASA needed a new flagship program that could be sold as practical and affordable. The answer was the Space Shuttle, a reusable spaceplane riding a big external tank and 2 solid rocket boosters, promising up to 60 flights per year, cheaper access to low Earth orbit, and a steady stream of science, military, and commercial missions. On the other side of the Cold War, the Soviet Union had lost the race to the moon, but not the appetite for prestige in orbit. They had focused on long-duration space stations like Salyut and later Mir, using the reliable Soyuz spacecraft to ferry crews. In July 1975, the Apollo-Soyuz test project brought American and Soviet crews together in orbit, docking the 2 spacecraft and shaking hands for the cameras. Officially, it was a symbol of détente. Unofficially, Soviet military planners came home more suspicious than reassured. As details of the shuttle design became public, they saw features that made little sense for a purely civilian vehicle. The American orbiter's large delta wings were designed to provide cross-range capability, allowing it to re-enter and reach alternate landing sites after a single polar orbit. The payload bay could carry massive military satellites, or even retrieve and return them. The 3 Space Shuttle main engines were powerful, sophisticated, and deeply tied to U.S. Air Force requirements. To Soviet eyes, this looked less like a peaceful truck and more like a potential weapons platform, able to launch quickly, grab or disable satellites, or deploy experimental payloads with minimal warning. In a system defined by worst-case thinking, that possibility alone demanded a response. The Soviet leadership gave the order in 1976 to start their own reusable shuttle program, officially called Buran, meaning snowstorm. Unlike earlier contests in nuclear weapons or ballistic missiles, copying the American design no longer required stealing deeply classified blueprints. Much of NASA's technical material was openly published or accessible through scientific networks and government libraries. KGB and military intelligence officers learned to exploit early computer networks, harvested document reference numbers, then persuaded or paid local staff to print copies of unclassified reports. Over several years, they collected thousands of pages on aerodynamics, thermal protection, flight software, and materials. Even with that trove, Soviet engineers could not simply photocopy a shuttle. Their factories, alloys, test stands, and industrial culture were different. They took the American layout as a starting point but made key structural changes. The most visible similarity was the orbiter's overall shape. A blunt black nose, white fuselage, double delta wings, and a large payload bay. The real divergence sat in the propulsion architecture. NASA's orbiter carried 3 main engines on its tail, feeding from an external tank, and used 2 giant solid rocket boosters strapped to the sides. Those solids provided most of the liftoff thrust but could not be throttled or shut down once ignited. The Soviet design team saw those compromises and went another way. They removed the main propulsion system from the orbiter entirely and turned it into a pure glider for the ascent phase. All high-thrust rocket propulsion moved onto the Energia launch vehicle, a modular super heavy booster built around a hydrogen-oxygen core and 4 kerosene-fueled strap-on stages. Each strap-on, essentially a Zenit-class rocket with the mighty RD-170 engine, delivered enormous thrust with high performance and full throttling capability. Energia could lift around 100 metric tons to low Earth orbit, comparable to the Saturn V, whether the payload was Buran, a large satellite, or a military platform. For atmospheric testing, the Soviets built a separate Buran analog fitted with 4 jet engines, allowing runway takeoffs and repeated landings like a conventional aircraft. That vehicle, not the orbital flight article, performed dozens of approach and landing tests. The real Buran orbiter that flew to space in 1988 remained an unpowered glider on re-entry, similar to the American shuttle, but the jet-powered testbed reflected the Soviet emphasis on verifying behavior in real hardware, rather than relying solely on simulation. Where NASA had the lifting body test flights of Enterprise dropped from a Boeing 747, the Soviets had their own jet-assisted workhorse. Energia's first launch came in May 1987 without Buran on its back. Instead, the payload was Polyus, also known as Skiff-DM, a roughly 80-ton experimental platform intended to test anti-satellite and directed energy technologies. Energia functioned almost perfectly, but Polyus failed to execute its orientation maneuver correctly after separation. Instead of rotating 180 degrees before firing its engine to circularize its orbit, the spacecraft continued a full turn and fired in the wrong direction, dropping itself into the Pacific Ocean. For the engineers, it was a brutal reminder that even flawless boosters cannot save broken guidance logic. On November 15, 1988, Energia and Buran finally flew together. The mission launched from Baikonur's Site 110 in Kazakhstan under cold, windy conditions. There were no cosmonauts aboard. Buran 1.01, the first flight-ready orbiter, was controlled entirely by onboard computers and ground commands. Energia pushed the stack into orbit, the orbiter separated, and Buran completed 2 circuits around the Earth at an altitude of roughly 250 kilometers. It then executed a deorbit burn using its orbital maneuvering engines, descended through the atmosphere, and lined up with the Yubileyny runway at Baikonur. The landing was the kind of achievement that test pilots usually dream about, and no pilot was on board. In gusty crosswinds, the automated system brought Buran down safely on its first and only orbital mission. From a purely technical viewpoint, the Soviet shuttle program had demonstrated the core capabilities it was designed for: heavy lift flexibility through Energia, and a reusable orbiter capable of precise, unmanned operations. On paper, the Soviet answer to the American shuttle was at least as capable, and arguably cleaner in its separation of roles. The problem was that the world around Buran had changed faster than the engineering could keep up. By the late 1980s, it was increasingly clear, even in the United States, that the shuttle had not delivered on its promised economy or launch cadence. Instead of 60 flights per year, NASA was averaging only a handful. Each orbiter required months of inspection and refurbishment, and the Challenger disaster in 1986 had exposed the fragility of a system that mixed human passengers with large solid boosters and limited abort options. Meanwhile, robotic expendable rockets continued to do most of the work of placing satellites and probes. The Soviet Union had an additional advantage. Soyuz never went away. While Buran consumed enormous resources in materials, facilities, and personnel, Soyuz continued to launch crews to the Salyut stations, and later to Mir using comparatively modest rockets. When planners weighed the future, they saw a choice between an unproven, extraordinarily expensive shuttle system and a well-understood capsule paired with conventional boosters. Against the background of perestroika, economic stagnation, and political upheaval, the calculus shifted from prestige to survival. After the single 1988 mission, Buran never flew again. Official cancellation came in 1993, after the Soviet Union had already dissolved and Russia was struggling to pay for even basic military and civil programs. The Energia Buran infrastructure at Baikonur, including huge assembly buildings and specialized equipment, fell into slow decay. The flight orbiter Buran 1.01 and a full-scale Energia mock-up were stored in the MIK assembly hall. Maintenance budgets shrank, inspections were deferred, and water leaked through the roof. In May 2002, after years of neglect and structural corrosion, The roof of that hall collapsed during repair work, killing 8 workers and crushing the orbiter and booster mock-up beyond repair. Other pieces of the program met kinder fates. One atmospheric test vehicle eventually traveled to a German museum, where visitors can walk under its wings and imagine a future that never happened. Several incomplete orbiters and structural test articles remain in storage at Baikonur and elsewhere, occasionally photographed by adventurous explorers who slip past fences and dust off the relics. Yet for all of the romantic ruin imagery, the essential story is not about tragedy. It is about how complex national projects live or die on sustained logistics, not on single spectacular missions. The contrast with NASA's shuttle fleet is instructive. The United States kept flying shuttles until 2011, carrying out 135 missions over 30 years, including satellite deployments, Hubble Space Telescope servicing flights, and assembly of the International Space Station. But even there, cost and complexity remained stubborn. Each launch demanded a massive workforce at Kennedy Space Center and related facilities. After the Columbia accident in 2003 caused by foam shedding from the external tank that damaged a wing leading edge, the limitations of the design became impossible to ignore. The shuttle was retired without a direct successor of the same form. Instead, both the United States and Russia leaned harder into simpler architectures, capsules on top of rockets with clear separation between crew vehicles and heavy cargo lifters. Soyuz kept flying crews to orbit. The United States eventually fielded commercial crew systems like SpaceX's Crew Dragon, riding reusable boosters but keeping the crewed spacecraft itself compact and relatively straightforward. Heavy payloads moved on expendable or partially reusable rockets. No one rushed to build another winged spaceplane with an integrated main propulsion system bolted to its tail. In a sense, Energia anticipated the modern approach to super heavy launchers more than the shuttle did. By concentrating all high-thrust propulsion into a modular core and strap-ons, it created a flexible platform that could, in principle, support many different payloads. Modern concepts like SpaceX's Starship and NASA's Space Launch System share that emphasis on powerful boosters and specialized upper stages or spacecraft, rather than a single vehicle that tries to be airplane, space station builder, and satellite truck all at once. The lesson from both shuttle programs is straightforward. Reusability only makes sense when the upkeep is cheaper than building something new. Buran's story is therefore less about failure and more about timing and priorities. The engineers succeeded at most of the challenges they were given. They built one of the most capable heavy-lift stacks ever flown, and demonstrated a fully autonomous orbital flight and landing long before modern autopilot systems became common. What they could not do was bend economics or politics in their favor. When the Soviet state that had commissioned the program collapsed, so did the financial and industrial network needed to support it. A reusable orbiter, sitting idle under a leaking roof, is just another liability on a shrinking balance sheet. Looking back, it is tempting to romanticize the lost potential of Energia and Buran, to imagine fleets of Soviet shuttles serving massive stations or building deep space ships. The historical record points in a different direction. Even if the Soviet Union had survived, the combination of high refurbishment cost, low launch cadence, and the availability of cheaper capsule missions would have pushed decision-makers toward a gradual wind-down. In the end, the Soviet shuttle project answered the American shuttle on technical and symbolic grounds, but shared the same underlying problem. It was a beautiful solution to a question that reality had already begun to move past. Completely.